Thank you. Can you guys all hear me in the back? Yeah? Great. Thanks. So, regression. Hopefully, most of you are aware of what it is. It's the classic problem, right? We have some correlated data. OK, let's predict one variable using another. Maybe we want to predict a user's activity level given their age. Maybe older people become more sedentary, and we want to sort of track that. Maybe we want to predict a patient's cholesterol from their BMI or consumer spending from their salary. These sorts of problems vary across domains. They're pretty universal. And you sort of expect, OK, my data will look like this. There'll be some noise, but largely I can just sort of pass a line through it, go into Excel or Python, whatever, and it'll work. And so how does this work? Well, there seems to be a trend, so we can fit a line. So if there were a perfect line, it would satisfy this system of equations where if you took, say, an A0 or an A1, and for every data point, yi would equal A0 plus A1 xi. And you can stack all these equations and solve them and find your best solution. And you can also reformulate this as a matrix problem. This simplifies a lot of the math. And so if you multiply this matrix out, you'll see you're getting the same exact system of equations. All I've done here literally is taken what I had before and just shoved it into matrices. It's doing the same thing. And so when you run a linear regression, what you're typically doing is you're minimizing the square of the residuals. So you take your actual, subtract your predicted, square those, and take the sum. And this is what you're trying to minimize. And that's why it's called ordinary least squares, is because you're literally minimizing the sum of the squares. And in matrix form, it's a similar thing, right? We're just multiplying, putting that matrix solution in there. And this is what it looks like. And for notation, I'm just going to call that x matrix, the matrix of 1s and x's phi, and our a vector just a. And so it turns out, after a bit of either matrix calculus or algebraic manipulation, depending on what suits your fancy, you can actually, there's a closed form solution for A. And this is, whenever you're running a regression, this is basically what it's doing. It's computing something like this. And so what this does, it tries to find the best solution for your system by minimizing the sum of the squares. And this extends up to n dimensions. So if you have n dimensions and n data points, you have an exact solution. Otherwise, you sort of have to solve the least squares problem. And so at the end of the day, you get something like this. A line that goes through your data. I did this in Excel embedded in PowerPoint because I wanted just a quick solution. And you get some numbers, and you're happy, and your day's done. The end, talk over, let's go home. But that's not the case in pretty much every circumstance. So the real world's never really this nice. There's that whole data pipeline, right? You don't just magically get clean data. And even when you have data, a lot of times the data can be garbage. So users can intentionally provide incorrect information. They can unintentionally provide incorrect information. Maybe they just don't change the defaults. Maybe your ETL pipeline, which is taking data from sort of the raw production servers and shoving it into your data warehouse, has a bug in it, et cetera, et cetera, et cetera. This can go on forever. There's a million different things which end up basically just mucking with your data and screwing it up. And so the end result is you're going to have noise in your data that it can often break your regression. You need to be careful of this. And so something like this often looks something more like this. So you see this vertical line right around age 50. That's just if you had a birth date of January 1st, 1970, which ends up being the default for a lot of systems. Or maybe you have a bunch of zeros in there because your ETL pipeline's broken. Or maybe there's just one really extreme point. There's some 85-year-old user of your system when everyone else, when it's targeting like 20 to 25-year-olds or something. Or maybe even people just input their age incorrectly or something and see if something gets just shifted over. And so all these sorts of issues can arise, and they can all break your system in various ways. And so as you go through, you want to try to be robust to these things. And so your first instinct is probably, OK, well, let's just filter the data. In those cases, we can probably just knock out all of those bad points and probably be fine. And in most cases, that's you definitely want to try this, right? It's definitely a good first pass to do. And you certainly will be able to eliminate some of the outliers. But there's some where you're just going to have problems, and you're not really going to know what's going on. So say you're looking at weight. Was the user 120 pounds or 120 kilograms? Both are very valid weights. maybe you have a tall person who's skinny. Maybe you have a shorter person who's more portly. They're both valid. Was that person really born on January 1st, 1970? Some of us probably are. That's a very valid birth date. And so these things go on and on. And to make matters worse, when you start getting to larger data sets, the data can really mislead you, especially if you're trying to visualize it. So this is a plot of the same data. On the left, I just did a scatter plot in Matplotlib. On the right, I plotted it as a histogram. And with the lighting, you probably can't see it. But really what happened was there's a few speckles outside of that really bright yellow band representing the data that sort of makes it look like a rectangular blob. But really, it's just a line. And sort of because of the data point, there's so many data points, you don't really get a good sense of the density of the data. And so even when you're doing this, you need to be careful because you can personally screw up your data by filtering out things that are actually inliers. And so, as you can see here, this is a 10-to-1 inlier to outlier ratio with only 110,000 points. And if I were to look at that to start and didn't create a heat map, I wouldn't, at first glance, that might look like there's no relation at all, when clearly there's a very strong one. And so after a few hours of cleaning, you get to feel something like this, and you just want to give up, and you're not having a good day at this point. So maybe your response is like, screw it. I'm just going to run the regression anyways, see if it works, and maybe it will, and I'll be happy, and life will be hunky-dory. It turns out you often can't just do that, though. Least squares regression is very, very brittle to outliers of all sorts. And so the question is, A, why? And B, can we fix it somehow? What can we do to sort of eliminate those issues? And here's a few examples. So say we're looking at age. This one user who, whatever the value of interest is, because they're so much older, they're having an outsized influence on our regression. Just looking at that data, it's very obvious what the best line should be, right? However, this one user is completely skewing it. Same for incorrect units. Say we had a group of 5 or 6 users who just entered their weight in kilograms instead of pounds, not realizing it. Your line gets skewed again when clearly the data is following. There's a very strong linear trend. Default values, similar issues, right? The whole line gets shifted up because we have all these people born on January 1st, 1970. And so the question becomes, before we can even try to fix it, let's try to formalize what's going on. And so to do so, we can define what makes a point so powerful that it's able to break these things. And one way of doing so is to define what influence is. And if you remember, we're trying to minimize the sum of the square errors. So this sum of RIs, our residuals. And so if we take the derivative of that, that's basically telling us if we just nudge that residual a little bit, if it gets slightly bigger or slightly smaller, how much is it going to affect our total loss, the thing we're trying to minimize? And so we take the derivative, and we'll just give it a name, psi. And it turns out it's just 2 times the residual itself. And so what's problematic about least squares is that as your residual grows, if you just nudge it just a little bit, the effect of that little nudge gets bigger and bigger as your error gets bigger and bigger. And so these outliers become more and more influential and have a bigger and bigger impact on your regression itself. And so the natural question is, well, can we just develop a loss function other than sort of that squared residual error that doesn't have such a property? And that's where M estimators come in. So what we're going to do is, we know that quadratic loss just hurts us too much, especially for big errors. So can we do something to sort of limit their effect? And that's what we're going to try to do. And so if we just plot a quadratic loss, you can see it's just sort of growing and growing, getting steeper and steeper as you move away from 0. And we wanted something whose rate of growth is bounded as opposed to growing. And so if we could just sort of, if you can imagine like just grabbing those tails and sort of bending them down, that would pretty much solve our problem. And that's what we're going to try to do, is create some function instead of just the square that gives us this nice property. And so, what kind of function are we looking for? There's a few properties you probably want to have that make intuitive sense, right? So because we're trying to minimize the sum of this function for all of our residuals, we want the function itself to be non-negative. Otherwise, if a value could create a negative output, you would always want that negative output, and you could theoretically just make your sum go very, very small. You want to have a minimum at 0. So if you perfectly predict the point's output, you don't want to be worse than predicting it with some error. So minimum at 0 also makes sense. Symmetry. So if you're off to the left or off to the right, shouldn't really matter. And finally, monotonic. If your error grows, it should always be worse than if a smaller error, basically. So you want these, these nice properties, and they sort of all make intuitive sense. And so now, instead of minimizing the sum of the residual squared, we're going to minimize the sum of this function of the residual. And the question now is, what kind of function does this for us? And so how would we even do this, first of all, for any function? And so if you just take the derivative and set it equal to 0, the standard procedure for finding a minimum, you get this sum of just, and this is just the chain rule of calculus, so this d rho dr times dr dA. Or using our notation from earlier, where rho was just our loss function, it's, we have 5r times dr dA. And so just did some math, and this is what we're going to need to solve once we pick our loss function. And I'm going to do a little bit of mathematical trickery here. I'm going to define a w function that is just this phi, or psi rather, divided by r. And that gets us nowhere, right? It doesn't actually change the problem. But what it does do is this formulation you see right here, this is the exact solution, or this is what you're trying to solve when you're trying to solve a weighted least squares. And so what we've done, in essence, is we've said, OK, least squares doesn't work well for us because the error grows without bound. So what we're going to do is we're going to say, we are going to convert this into a problem. We're going to minimize a different loss function that has better properties. And we're going to take that loss function, and we're going to convert it into a weighted least squares problem where the weights are going to depend on sort of the residuals themselves. And so we now have an easy way of solving this. And a nice property that we're looking for to sort of make it robust is as these residuals grow to infinity, we want these weights to get small so they have no impact on the regression itself. But we've introduced a new problem in doing this. We want these w's for the weighted least squares regression, but w depends on r, the residuals. And the residuals depend on your coefficients of your regression. And those coefficients depend on the weights. And so you have this big loop. And the question is, how do you break it? And so there's one pretty standard technique for doing this. It's called iteratively reweighted least squares. So what you do, start with a standard linear least squares solution. Just get something to compute those residuals. Compute your weights. From the weights, solve for a new set of regression coefficients. And then from the regression coefficients, compute a new set of residuals. And just keep doing this over and over again. And eventually, you'll converge. And so this is a pretty simple, fast, and robust way of doing it. And I'll show you one of the reasons why it's so fast. I'm going to show you right now. So earlier, I showed you that if you just wanted to solve a least squares problem, it basically comes down to this closed form solution. You just multiply these matrices out, and you get your regression coefficients. It turns out, if you're doing weighted least squares, all you need to do is just shove this W matrix in there in the right place. And once you do that, your problem's solved. So it's, again, basically you're going to repeatedly compute this over and over again as you iterate. You're going to compute W's, solve this, compute residuals, and just keep going. And so the most common version of this is the Huber loss function. And so this is pretty much like if I asked you what's the first thing you do to try to fix this, this is probably the one you would come to. So we like that sort of quadratic shape, but we don't like how it gets really steep at the edges. So screw it. Let's just make them lines at the end. It's exactly what this function is. We just say we'll replace that at some point. We'll replace the quadratic with linear segments. And those linear segments will have the same slope and value at the points where they switch over from the quadratic to the line. That's all it's doing. It's making sure the function itself is continuous, and the slope is also continuous. And if we look at the weight function, you can sort of see what the effect of this is. When you're within this threshold, k, of the origin, your weights are constant, just like a normal least squares problem. But as your residuals grow, your weights taper off to 0. And so that's how this allows you to sort of limit the effect of these large outliers. And so you see here, maybe you don't. Oh, PowerPoint crashed. Nice. All right, let me see if I can. Oh, now it's reopening on me. Continue, I guess. Great. All right. Fun times. Yeah, there we are. So, as you can see here, before, if we use a ordinary least squares, this 1 point kills our solution. However, by just changing the loss function, right, and just computing it this slightly different way, we're now suddenly way more robust. And our line largely fits the data. You know, it's not perfect, right, but it does a pretty good job. And so there's a whole set of these sort of M estimators that you can use, these different loss functions that you can use. And these slides are going to be online, so don't worry about trying to jot any of this down. But at the end of the day, I sort of want to give you a general sense of what's going on. So the base, you see sort of the standard loss function is the residual squared. And we looked at Huber, where we sort of just capped off the ends with lines, so they didn't grow as fast. Some of these other functions actually have very different properties, where they can actually saturate to a certain value. And that's, so not only does the residual stop affecting the regression, its influence just completely dies away. And you can sort of see this in the influence function themselves, where if you look in sort of that third column for the bottom two rows, as R gets really big, those values get closer and closer to 0. Whereas for the Huber loss function, the influence remains constant. It gets capped. And so what does this look like visually? You can see here, if you look at the influence of the various loss functions, ordinary least squared, it just grows without bound, as we expected. For Huber, we say, OK, your influence gets capped at a certain point. For the other two, you can sort of see one of them smoothly decays to 0, whereas the other one actually goes straight to 0, not asymptotically. So Germain-McClure goes asymptotically to 0. The Tukey loss function actually goes directly to 0. So at some point, when the residual increases beyond a certain value, in this example 1, literally the point has no influence at all on the output of the regression. You tweak it a little bit, doesn't change what your loss function is going to be, or what your total loss is. And sort of the weights are just a similar thing of this. You end up dividing. And so one class, which I was just briefly touched upon, were these redescending M estimators, these ones that go to 0. So the Germain-McClure and the Tukey loss functions were both instances of this, because if we look back here, you can see their influence goes to 0. So as these residuals grow, beyond a certain threshold, their impact on the total loss decays to 0, which means they can be, if they're off by 10 or off by 20, it doesn't matter. Once they're beyond a certain threshold, they literally have no additional impact. And so it rejects gross outliers, which is great. It also avoids masking effects, so you're not intentionally or unintentionally fitting a bad line and then sort of screwing with that cycle. But unfortunately, because it's nonlinear, your solution isn't guaranteed to be unique. So if that's important to you, you have to be careful using these. If you run it 10 different times with 10 different initializations, you're not guaranteed to get the same exact line, maybe slightly different. For QA purposes, that may be challenging. Yeah?
How different is slightly different?
Normally it's not too bad, but depending on the data, if your data is really bimodal, you can sometimes catch different lines. So just to sort of recap this bit, when you're using ordinary least squares, you need to be really careful because it is highly sensitive. And sort of M estimators give you this alternative of things that are less sensitive, and it helps you out a bit. And based on your choice, you can either limit the influence of these residuals, as in a Huber loss, or actually reject them entirely with the Germain-McClure or the Tukey loss. And in general, you probably want to start with a Huber loss. It's the safest. You're not really going to screw things up. If it still doesn't work, maybe move on to use the other one. Now, sometimes this isn't even enough. Things still don't really work for you because your outliers are just so gross, you're really unhappy when this happens. And so what can you do? Again, we're trying to exclude these outliers, and we're trying our best to do so through filtering, through robust regression, you name it. And with M estimators, we're trying to do this. And we're able to control the effect to some extent. But is there another way? So let's start with a different set of assumptions. Before we said we want the loss function to really limit the effect of some of these outliers and not get dominated by them. What if we just a priori knew some of our data was complete crap? Like literally just garbage, some random noise got thrown into our system. And we just want to ignore it entirely, like not consider it whatsoever. And so if we could somehow identify the clean data, we could fit a model only to this subset. And that would give us the model we're looking for, right? Now, that's challenging, though. How do you identify the clean data itself? And so because it's challenging, let's just say, let's just fit a bunch of models to our data and see what happens. Maybe one of them will fit to the clean data. And so how would you do this? Well, basically take a subset of your data, fit a model to it, so say a line, and for each model, count the number of inliers, so the number of points that are within some threshold of your line that you define. And then once you do that, you basically do this over and over again for all of your models, and just keep the one that has the most inliers, the one that fits the biggest percentage of your data. And you get a final one that ends up fitting best. And once you do that, you fit this model only to the inliers. And then that's it. And this method is known as ransack. So one more time. You pick m points from your data set. So just some minimum number of points needed to fit your model. You say if it's a line, you fit a line. And then you say of all the data in my data set, not just the sample that I selected, how many of those are within some threshold? And then if this the number of inliers I have is greater than my best solution thus far, I keep it. And I just keep doing this for however many iterations I want, 100, whatever. And then finally, I just refit the model to all the inliers. So visually, pick 2 random points, draw a line. How many inliers do we have? OK, say 5. Let's try it again. Pick 2 random points. Now we have 10. And so we would just refit a line to all those points that fell within the sort of dashed regions. And now the problem is when we're doing this, there's a few different parameters we can tweak. One of which is sort of how many iterations do we want to go to make sure we get a good fit. Because we can just fit models all day, right? And eventually we'll get the right one, presumably. But you don't want to run all day. You want to make this fast. And so you have this probabilistic estimate where if you have some idea of how many outliers are in your data, you can actually estimate what is the likelihood of getting an inlier-only model. I don't want to walk through the probability of the sort of probability formulation of this, but if you think about it, sort of the likelihood of getting all inliers is just the likelihood of getting one inlier to the nth or mth power, assuming all your samples are independent. And so from that, you can sort of back out, what's the likelihood of getting at least one iteration that is all inliers. And from that, you can just solve for k, the number of iterations you want. And so this sort of informs you, gives you an upper bound on how many iterations you want to run for. Now, that being said, ransack, while nice because it just completely ignores outliers, does have a few drawbacks. So especially this noise threshold. So what counts as an inlier? You're setting this threshold, and anything outside of it gets completely ignored. And so if you set that threshold to be too small, you're going to be very sensitive to new points, for instance, because things that are actually inliers aren't being considered, and so you're going to be fitting to very small bits of your data. On the other hand, if you make that threshold really, really big, what happens is you now start to include some of your noise and some of those other things that you are trying to reject, those outliers. And now your model starts to skew and go in weird directions and you're not solving the problem that you're actually trying to solve anymore. And so there are variants that try to address these concerns by doing different things, but ransack itself is a pretty common method, and you'll hear about it a lot. Where do you see it? Where outliers can be large, so computer vision, faulty sensors, you name it. When cleaning data is often infeasible, multi-model fitting, implicit model fitting, you name it. And how do they compare to M estimators? Well, so first of all, they completely reject gross outliers, right? If you're not within that threshold, you're completely ignoring them. So this is similar to a hard redescending M estimator, but it's also a little different. And unlike M estimators, you're also able to fit implicit and explicit models. So when you're fitting that model, it doesn't have to sort of have that nice linear structure that we used earlier, because we were using iteratively reweighted least squares. You can actually fit any model, like a circle to some data, something implicit. And finally, there's additional tuning parameters. You end up with a bunch of parameters you have to tune that can affect the performance. And so, in summary, what are you going to take away from this talk? What should you try to remember? Your data is often quite dirty, especially when it's collected in a real-world environment. Only in the most controlled settings, so sort of those laboratory experiments, do you actually get really, really clean data. Anytime you're pulling data from a database, you should pretty much assume there's some amount of garbage in there that's going to break your stuff. And so you need to be careful. And so cleaning your data, it's half the battle. It'll get you part of the way there, and you should definitely do it to the extent you can, but it's nearly impossible to fully clean your data. And so you have to be careful when you're using these brittle methods, like ordinary least squares or anything like that. And so you should consider certain alternatives whenever possible. And so I covered some of them, but there's always others. So in case you ever want some more reading, there's other loss functions. As I mentioned earlier, there are these ransack variants that try to pick the best candidate solution in different ways. There's the Thiel-Sen estimator, which it's a really crazy one. It just computes all possible lines from all of your data points and picks the median and slope. And then, so it can be really computationally expensive as your dimensions grow. Least trim squares is just least squares on your kth fewest or your kth smallest residuals. You take like your 80th percentile of all your residuals and just run least squares on it. And then S estimators are sort of another variant of M estimators where instead you're trying to minimize a scale factor. But yeah, so I'm finishing a little bit early, so I'm going to take the time to plug that the place I work for is hiring. So definitely reach out to me either afterwards or on Twitter or LinkedIn, you name it. We're trying to grow pretty quickly, so if you're interested, definitely reach out. Yeah, with that, I'll take any questions. Yeah.
Thank you for the presentation. Just wondering, is there a degree of dirtiness where one set of methods is better than another set, like for very dirty data? And how do you define very dirty? Huber might be better than, say, ransack if it's...
Yeah, so there is a metric called sort of the breakdown point, if you want to Google that. And what that basically refers to is when your percentage of outliers grows beyond percent X, like what happens? Like when that percentage sort of varies based on the method. So in certain methods, if you hit like 30% outliers, things will break down. If you think about it, 50% is sort of like the upper bound. If you had more than 50% outliers, what are you fitting to at that point? You're fitting to, you'd rather fit to the noise than the data itself. So yeah, there are each method has different breakdown points, and there's sort of trade-offs between them as well, because in addition to breakdown points, people also sometimes look at sort of affine invariance. So if you sort of rotated your data, would you still get the same fit? And that's a nice property to have. So the combination of those two oftentimes dictate, sometimes which method you want to use. Yes.
Given the issues with the linear regression.
Sorry.
Sorry. Given the issues with the linear regression,
yeah.
At what point do you think you would want to switch to converting your continuous outcome variable you're trying to predict into buckets, categorical variables, and then using the methods you could use on categorical variables?
Yeah, so I mean, that's a very valid option for sure. I think it's going to be part of it's going to be context dependent, right? So for certain business use cases, you can do so, and others, maybe not. And in terms of, that does also help with robustness because a misclassification error is a misclassification error. I mean, I don't really have a good answer. I think it's almost like a smell test, right? If it smells like it's okay, sure, you can try it, and then you run it by the PM or whoever's managing the project. Yeah, I don't typically, I don't know, that's not normally one of my go-tos. I like to, if the problem is, if you want to have a regression problem, if noise is your problem, I try to find a better regression or clean my data better rather than try to convert it into categorical. But that's a very much personal preference thing. Doesn't mean it's not a valid option.
Question here. On the Huber method, you have a parameter k there.
Yes.
Is that you just treat that like a free parameter, or it's going to depend on your data? So
yeah,
I
for sure.
could imagine you do an ordinary least squares and then maybe do some statistics on the residuals and set k depending upon how many SDs above the mean or something.
Yeah. So there's a couple different things you can look at. So there's, like, theoretically speaking, there's a best value that is scaled relative to your data in terms of certain properties. And so there's a default value, I think, of like 1.3 something that you should just use unless you find things aren't working. That being said, it can be treated as a hyperparameter just like any other. And if you have, you can run cross-validation on it and see which one gives you the best result in sort of your validation set as well.
No, I'm just thinking about codifying it where I don't want to intervene. I'd have to do
I mean, if you don't intervene, you can, cross-validation is pretty hands-off, right? You pick a metric and just give some black box grid search saying, try different Ks for me. There were a bunch of questions in the back. Green jacket? Sorry.
Could you say something about the difference between true data that really is dirty, that's an actual point you want to exclude, and data that's an outlier but is really just a different regime? For example, in meteorology, we have the issue between persistence, when there's not much change, easy to forecast, and then the big changes that are rare, but everyone wants you to get that right.
Yeah, so I think that's not to try to use this as a crutch, but oftentimes that's also problem dependent, right? So in your issue, that's very much the case. Previously I worked at Fitbit, right? And one of the things we had were people running with GPS data. Mm-hmm. And sometimes you would see people running in the middle of the ocean at ridiculous speeds because they were either running on a cruise ship, like running laps around a cruise ship, or they're on their boat or in their car, whatever. Like, people do crazy things. Users unintentionally are malicious. Just assume that all the time. And so it's hard, right? Because if you set this threshold to completely reject outliers, you're now saying this event that I care about doesn't exist, which is the exact opposite of what you want to do. Mm-hmm. So yeah, I think there are certain cases where if those 5 or 6 sigma events are really what matter, be careful doing this because you're going to completely ignore them. Mm-hmm. And yeah, so sometimes I think filtering data in those circumstances, trying to eliminate the noise while also keeping those really extreme events is hard, and it probably requires human intervention or some sort of domain knowledge that you have to pull in.
We are fortunate that our data sets tend to be somewhat smaller, so that helps, but
Yeah.
still not easy.
Yeah, no, I don't think that's a simple problem.
Yeah. Thank you.
Yes.
Hi, just a quick question about the ransack method.
Yes.
If you have 2 models that have the exact same inline account, are there other parameters you can use to determine a more superior model, or are they just equivalent in this case?
I mean, if you wanted to create that would be one way of creating a variant. Typically, if you just take the out-of-the-box solution from scikit-learn or whatever, I think it's just going to take the first one that had the most.
Thank you.
So can you speak to the multi-dimensional data sets and if they present any particular challenges, since all the examples you showed were 2-dimensional?
Yeah, sure. So in terms of the M estimators, one of the things you can have when you start dealing with really large data sets or computing those matrix inverses can be really expensive. So it scales, I think, as n cubed. So there are iterative solutions to actually solve the least squares problem itself, and that would be embedded in a larger iterative task of trying to find the weights that sort of lead to a convergence. Now in ransack, it's a different problem of you need to fit a bunch of models, right? And so when you have a bunch of parameters, typically fitting those models are more challenging. You need larger samples, and the odds of getting the odds of guaranteeing an inlier-only model can become more challenging.
Thanks.
There's 2 people back there, yeah.
Yeah, I wondered if you could speak to extreme outliers in your outcome variable.
Can you provide a bit more context?
Let's say you're modeling, in this case, fire rates by census tract, and you have some census tracts that have few people, or you have an extreme outlier with one census tract that just has a lot of fires. Are there techniques that you can use along these lines to help with that? Because the outliers may pull your estimates.
Yeah, I mean, I think fundamentally what these methods are trying to do is not get pulled by those outliers. So ransack will completely ignore it if the estimate just ends up being way out there, or some of these other estimators will either limit the effect or also reject it. Yeah, I think sort of at the end of the day, if you're trying to model something and there's fundamentally like this bit of information you don't have that creates this huge swing, like are you in this certain district and you don't have that information, or it's only applicable to one data point, modeling it's hard unless it's a time series and you're tracking that one district over time. I think he was raising his hand earlier. Oh, no, in front, sorry. Oh. Right, yeah, there you go. Right next to you, to your left. There you go.
Hi. So it looks like there's a lot of different weighting schemes for your residuals. Is there like a rule of thumb for like how you select the optimal weighting scheme?
Are you talking about the M estimator, so the loss functions, or what do you mean?
Yeah. So for every loss function, there's like a different way you use the residuals to like do the weighting, right?
Yeah.
How would you go about selecting the optimal scheme?
Yeah, so typically, I don't want to get into too much detail, but those Ks are pretty normally specified with respect to if you passed in a normal distribution, you want certain properties to be maintained. Mm-hmm. And so they give you like a default K pretty much you can use that you can deviate from, but like if your distribution is roughly supposed to be normal with some outliers, you prefer to set the K to this value. Okay. And it's often normalized based on the scale of your data. So you can normalize your residuals by like a standard deviation and use this single K that just makes sense.
Okay, so this is like convention?
Yeah, it's convention. It's also just from statistics. It can be theoretically nice, but there's no need or reason to keep to it if you don't want to.
Okay.
Yeah, it could just be something you cross-validate over as well.
Okay.
I think there's someone in the back, and then we can come to you.
Hi, I just had a question about the ransack. So if your outliers are poor, but they're poor for a really systematic reason, I can imagine that if you get a bad pull of your data, you can get a regression line that fits really, really well. And so your inliers are going to be really strong. So my question was, are there any variants of ransack that try and take into account the fact that there may be systematic reasons that your outliers exist and selecting which of the models are the appropriate models?
Yeah, so I think part of that is, so when you fit the model, when you fit each individual model in the iterations, right, the metric of goodness by default is just the number of points that are inliers. And so if you have more outliers than inliers, which, I mean, at that point, and there's a systematic bias in those outliers so that you can actually predict what the outliers are as well, fundamentally, it's almost hard to say, like, fit this one set of data other than the other. That being said, because you basically have two lines and you're trying to pick one. There are some ways of doing it. One is you can fit one model, pull out the data, and try to fit the other. Another is some of these sort of variants include you can apply a prior to what things should look like, And using that prior, it sort of biases towards one set of, if you had two lines or parallel, one line rather than the other. Was there another question over here? Nope. OK, I guess right here then, yeah.
In cases like that?
Yeah, so the question was, can you apply the methods with a mixture model? So in multi-model fitting, what you often end up doing is fitting one, pulling out the data, and fitting another. You could theoretically fit it as well. I mean, because at the end of the day, when we fit a line there, there's no reason it has to be a line. It just has to be something that we fit and something that we can count inliers to, where we define inliers in some way. So what you're fitting in that fit chunk can be anything. So if you want to try to fit a Gaussian mixture model, sure, that'd be possible. You just need to be able to count inliers afterwards.
I meant more like you have a separate model for the outliers and a weighted sum over the two models. It's essentially a kind of a boosting. Can you boost with this?
Can you boost with ransack? I'm trying to think of how that would work. So you're saying if you have a separate weighting scheme for the outliers, and then I guess I'm not seeing the path you're describing.
We'll talk about it later.
Yeah, we'll talk about it offline. I don't know. Do you guys know who had their hand up first? You guys can figure it out.
One of the things I've been wondering about is alternate definitions of the residual.
Yes.
Yeah, being function of x versus x, that's your classic residual. But you could also look at it as normal plumb line to the linear fit, or you could look at it as a percentage of the base value. Have you seen improvements by defining the residual differently?
I mean, I think it would probably depend on the domain, right? In some instances, if you can imagine taking a log transform, which would be equivalent to sort of looking at ratios almost, and maybe that would make sense in a certain, if something like a compounded interest use case, like what is the best something that just ends up being multiplicatively applied rather than additively applied. But I mean, yeah, I personally haven't done that, but there's no reason why you couldn't either.
Can you include the loss functions here in models like ElasticNet that penalize the coefficients at the same time? Or?
Yeah, I mean, at the end of the day, if you wanted to regularize, so for elastic nets, maybe not. For ridge regression, where you have an L2 penalty, yeah, it would just fit inside the inverse compute. You have your plus gamma, which is your regularizer. Yeah. All right. I think I have 2 minutes or 2 questions. I don't know.
2 minutes.
2 minutes. All right. Are there any last questions? Otherwise, here we go.
Do you have a favorite, reference on this, intro or other type of thing that you like to look at or you'd recommend?
So there's a book called, I think, Robust Statistics that came out in the last, I forget when it came out, but I think it's by a guy named Rousseau who's pretty good. There's also, so all of these methods are all in scikit-learn as well. And scikit-learn's documentation is pretty solid, especially for an open source package. The Huber regression is actually a pretty recent addition. I don't think they have some of the other loss functions though, but stats models may if you're a Python person, so you can check that out as well. All right, I want to make sure the next presenter has a chance to get set up, so thank you.